The sun is sinking beyond the open ocean, light weakens across the surface, and the water below becomes darker by the minute. Waves move above a world that remains mostly unseen, cold currents rise from depth, and the last silver fish disappear into blue shadow. Far beneath the surface, a large shape moves through the water. It does not hurry, it does not need to. This is the great white shark. Its scientific name is Carcharodon carcharias, and it is one of the most recognizable predators in the ocean. The body is broad near the head, narrow toward the tail, and built for a balance of power, control, and long-distance movement. The upper surface is gray, the underside is pale, and the division between them helps the shark disappear from more than one direction. From above, the darker back blends with deep water. From below, the pale underside merges with light from the surface. This pattern is known as countershading. The great white continues forward, water passes through the mouth and across the gills, and the ocean opens around it. Chapter 1: A body built for the open ocean. The great white shark belongs to a group of fishes with skeletons made mostly from cartilage. Cartilage is lighter and more flexible than bone. It forms the internal structure of sharks, rays, and their relatives. The body of a great white is shaped like a powerful spindle, broad through the middle, tapered at both ends. This form reduces drag, it allows efficient movement through water, and it supports sudden acceleration when a hunt begins. The tail is crescent-shaped, the upper and lower lobes are nearly equal in size, and each sweep transfers power into forward motion. Strong muscles run along the body, they contract from side to side, driving the tail through the water. The pectoral fins extend like wings, they do not flap instead, they create lift and help control direction. Unlike many bony fishes, sharks do not have a swim bladder. Lift comes from the fins, the shape of the body, and a large oil-rich liver. Movement helps prevent the animal from sinking. The skin is covered with tiny tooth-like structures called dermal denticles. They point backward, and they help water move smoothly across the body. To the touch, shark skin can feel rough in one direction and smoother in the other. The denticles reduce turbulence, and they also protect the surface of the body. Every feature works together: tail, fins, skin, muscle, and shape. The great white is built as a complete system for life in moving water. Chapter 2: The senses of a predator. The ocean is a difficult place to search. Visibility changes with depth, weather, and suspended particles. Sound and scent travel differently than they do on land. The great white shark relies on several senses at once: vision, smell, hearing, pressure detection, and electroreception. Each provides a different part of the surrounding world. The eyes are well developed. A reflective layer behind the retina can improve sensitivity in dim conditions, and the shark can detect contrast against the surface. Vision becomes especially important during the final moments of an approach: the outline of a seal, the flash of a fish, the movement of prey against open water. Smell can reveal substances diluted across large volumes of water, a wounded animal, a feeding event, or a trail carried by current. The information may come from far away. The nostrils are used for smell, not breathing. Water enters sensory openings beneath the snout, then passes over tissues that detect dissolved chemicals. The shark also detects low-frequency sounds and vibrations. Struggling fish create irregular movement, and those disturbances can travel through water. A line of sensory organs runs along the sides of the body. This lateral line system detects pressure changes and nearby motion. It helps the shark understand movement beyond direct sight. Small pores around the snout lead to organs called the ampullae of Lorenzini. These structures detect weak electrical fields, including signals produced by the muscles and nerves of living animals. At close range, electrical information can guide the final strike. Even when prey is partly hidden, the shark senses a living body within the water. Chapter 3: Teeth that are always replaced. The mouth of a great white contains several rows of teeth. Only the front rows are used directly during feeding. Rows behind them wait as replacements. Each tooth is triangular, the edges are serrated, and the shape is adapted for cutting flesh. A tooth may be lost during a strike. It can break against bone or pull free while prey struggles, but the loss is temporary. Replacement teeth move forward over time. A continuous system keeps the cutting edge ready, and a shark may replace thousands of teeth during its life. The jaws are not fused rigidly to the skull. They can move forward during a bite, increasing reach and control. The upper jaw lifts, the lower jaw rises, and both sets of teeth enter the prey. The bite is powerful, but the function of the teeth is not only crushing, their main advantage is slicing. A large piece of tissue can be removed quickly. The shark may then release, circle, and return. This method reduces the time spent holding dangerous prey. Seals can bite and strike back. Large fish can twist violently. The teeth are famous, but they are only one part of the hunting system. Approach, timing, speed, and sensory control are equally important. Chapter 4: Warm muscles in cold water. Most fishes have body temperatures close to the water around them. Great white sharks can keep parts of their bodies warmer than the surrounding ocean. This ability is called regional endothermy. Special arrangements of blood vessels help conserve heat. Warm blood leaving active muscles passes close to colder blood returning from the gills. Heat moves from one vessel to another. This countercurrent exchange reduces heat loss. The swimming muscles remain warmer, and performance improves in cold water. The stomach and parts of the brain may also remain warmer than the surrounding sea. Digestion can continue efficiently, and sensory systems can function in cold conditions. This adaptation allows great whites to hunt in temperate and cool regions. They can follow seals, tuna, and other prey even when surface water is cold. Warm muscles contract with greater power. They support long travel, and they can produce sudden acceleration. The shark is not warm in the same way as a mammal. Its entire body does not remain at one stable temperature. Heat is concentrated where it provides the greatest advantage. The difference may be only several degrees, but in the ocean that difference matters. It expands the range of conditions the animal can use. A great white can cross cold currents, dive into deeper water, then return toward the warmer surface. Its body is adapted not to one temperature, but to a changing ocean where heat, depth, and prey shift constantly. Chapter 5: Hunting from below. Near a rocky island, seals gather at the surface. They rest, enter the water, and return to land. The boundary between ocean and shore becomes a hunting ground. A great white patrols deeper water. Its darker back blends with the blue below, and the pale sky hides the seal's view upward. The shark approaches from beneath, not directly under every seal, but along routes shaped by current and experience. A seal at the surface is outlined against light. Its flippers move, its body creates sound and pressure changes. The shark increases speed, the tail sweeps harder, and the distance closes. In some locations, the attack becomes nearly vertical. The shark strikes upward, and both predator and prey may leave the water. This behavior is known as breaching. It is most famous in regions where great whites hunt seals near the surface, but it is not used in every hunt. The first strike may deliver a severe bite. The shark often releases, then circles while the prey weakens. This reduces the chance of injury from teeth and claws. A large seal can fight back, and caution remains important even for a powerful predator. Some attacks fail completely. The seal turns, accelerates, or reaches shallow water. The ocean contains no guaranteed meal. Chapter 6: Fish, rays, and other prey. Great white sharks are often associated with seals, but their diet is broader, and it changes with age, size, and location. Young great whites feed heavily on fishes. They may hunt rays, smaller sharks, and fast-moving schooling species. Marine mammals become more important as the shark grows. A ray resting on sand can detect movement above, but the shark can also sense the weak electrical field beneath the surface. The final approach may come from the side or above. Tuna and other large fishes offer speed rather than armor. The shark must match movement, then strike with precision. Carrion can also provide food. A dead whale becomes a major source of energy, and several great whites may gather around the same carcass. The shark removes large pieces, turns away, then returns when space opens. Scavenging requires less energy than chasing living prey. A whale carcass can feed many predators. and it supports an entire community of smaller organisms as it sinks and decomposes. Diet reflects opportunity. A coastal shark may encounter seals, an offshore shark may feed on fish, squid, or carrion. No single prey defines the species everywhere. Great whites are adaptable, and different populations use different food resources. The ocean changes by season, prey arrives and departs, and the sharks move with those patterns. Chapter 7: A Life of Long-Distance Travel. Great white sharks do not remain near one beach throughout life. Many travel across entire ocean basins, covering thousands of kilometers. Satellite tags have revealed movements far beyond coastal feeding grounds. A shark may leave a seal colony, cross open water, and return months later. Some individuals move between continents, others follow repeated regional routes. The pattern depends on population and ocean conditions. During long migrations, the shark passes through water with little visible structure. No trees, no mountains, no shoreline, only currents, depth, and the position of the sun above. Navigation may involve several cues: magnetic fields, smell, temperature, current, and memory. The exact combination is still being studied. The open ocean is not empty. Schools of fish move through it, squid rise at night, and drifting organisms follow currents. A great white may dive repeatedly during travel, descending into colder water, then returning toward the surface. These vertical movements may relate to feeding, navigation, or temperature regulation. Several explanations may apply at once, and behavior can change by region. Long travel connects distant habitats. A shark seen near one coastline may later appear far away. The same animal belongs to more than one local ecosystem. Protection in one place may not be enough. Migratory predators cross borders, fishing zones, and international waters. Chapter 8: The White Shark Cafe. In the northeastern Pacific, some great white sharks leave the coast of North America. They travel toward a region of open ocean between California and Hawaii, a place sometimes called the White Shark Cafe. The name does not mean the water is filled constantly with visible prey. The region is vast, and much of its biological activity occurs below the surface. Tagged sharks spend months there. They make repeated dives, and their movement patterns differ between day and night. During some periods, males perform rapid up and down movements. The reason is not fully understood. Feeding and reproductive behavior have both been considered. The water contains layers, warm near the top, cooler below, and deep communities rise toward the surface after dark. This daily movement is called diel vertical migration. Fish, squid, and other animals move upward at night, then descend during daylight. The sharks may take advantage of this shifting prey field, diving into deeper zones, then returning toward light. The White Shark Cafe remains one of the most intriguing parts of their annual cycle. The animals gather across a broad region, far from the coastal seal colonies that first made them famous. The behavior shows how incomplete surface observation can be. A shark that disappears from shore has not vanished. It has entered another part of its life. The open ocean keeps much of that life hidden. Tags reveal depth and movement, but the full purpose of the journey remains under study. Chapter 9: Social Behavior Without a Pack. Great white sharks do not form packs like wolves. They spend much of their time alone, but they are not completely without social interaction. Several sharks may gather around a rich food source, a whale carcass, a seal colony, or a productive current. The animals must negotiate space. Body size can influence access. A larger shark may approach first. A smaller individual may wait or circle farther away. Direction, posture, and movement also carry information. A shark may turn sharply, lower a pectoral fin, or move in a way that warns another animal. Direct fighting is costly, teeth can cause severe injuries, and avoidance is often safer. Bite marks are sometimes found on great whites. Some may come from mating, others from conflict or mistaken strikes. At feeding events, individuals can show repeated patterns. Some approach boldly, others remain cautious. These differences suggest distinct behavior between individuals. One shark may investigate a boat, another may remain deep. Social structure in great whites is still being studied. They do not create stable family groups, but encounters may be more organized than random. The ocean allows distance. A shark can leave a gathering and return to solitary movement within minutes. Chapter 10: Reproduction, the least seen chapter. Much of great white reproduction remains difficult to observe. Mating has rarely been witnessed, and birth has never been documented in complete detail in the wild. Great whites reproduce through internal fertilization. The male uses specialized structures called claspers, and mating may involve biting to maintain position. Females can carry scars around the body and fins. Some are believed to result from mating encounters, though scars can have other causes. Embryos develop inside the mother. They are not connected to a placenta in the same way as most mammals. Instead, they receive nutrition within the uterus. Developing young consume unfertilized eggs produced by the mother. This process is called oophagy. It provides energy before birth. The gestation period is thought to be long, possibly more than a year, but exact timing remains uncertain. Litter size is small compared with many bony fishes. Each young shark is already large at birth and begins life without parental care. There is no den, no nest, and no guarding adult. The newborn enters the ocean alone, equipped with teeth, senses, and instinctive behavior. Slow reproduction makes the species vulnerable. Females take years to mature, and lost adults are not replaced quickly. The hidden nature of reproduction remains one of the greatest gaps in white shark biology. Nursery areas offer clues, but much of the process occurs beyond direct observation. Chapter 11: The Nursery Grounds. Young great white sharks are often found in warmer coastal waters. These regions can provide abundant fish and fewer large predators. They are known as nursery areas. A nursery is not a guarded location. Adults do not remain with the young. The term describes habitat used repeatedly by juveniles. Shallow coastal zones can offer feeding opportunities. Rays, small sharks and fishes move across sand, and warmer water supports growth. Young great whites are smaller and more slender than large adults. Their hunting style reflects their size. Marine mammals are not yet the main prey. They may patrol beaches, bays, and continental shelves, often close to regions heavily used by people. This creates opportunities for observation and conflict. Juveniles can become caught in fishing gear, nets. Long lines and hooks do not always target them, but accidental capture can still be fatal. Tagging young sharks helps identify important habitat. Researchers track movement, temperature, and depth, then compare patterns across seasons. Some juveniles return to the same general areas. Others move along entire coastlines. Nursery use can be flexible. The early years are dangerous. Larger sharks may prey on smaller ones. Food availability changes and fishing pressure remains. Every juvenile that survives carries the future of a slow-growing species. Maturity lies years ahead, and the journey toward adulthood is long. Chapter 12: Growing into a giant. Great white sharks grow throughout much of their lives. Growth slows with age, but the largest adults are far heavier than juveniles. Females generally become larger than males. Large size supports reproduction, and it may allow females to carry developing young. Exact maximum size is difficult to confirm. Ocean animals are hard to measure, and estimates from photographs can be distorted. Reliable records place the largest great whites at more than 5 meters. Some may exceed 6 meters, but extraordinary claims require careful evidence. A shark of this size is not simply a scaled-up juvenile. Its diet changes, its travel patterns may change, and its position around food changes. Large adults can hunt seals with greater power. They can remove larger pieces from carrion, and smaller sharks may give them space. Scars accumulate across the body, marks from prey, other sharks, fishing gear, and unknown events. The skin becomes a record of survival. Older sharks have crossed many regions. They may return to familiar feeding sites, using routes learned across years. Age estimation remains difficult. Scientists examine growth patterns in vertebrae and other tissues, but methods have changed as new information appears. A great white's life may extend for several decades, possibly much longer than once thought. the ocean journey can span a large part of a human lifetime. Chapter 13, Breaching, the famous leap. Few images are more dramatic than a great white leaving the water. The body rises beneath a sealed momentum, carries both predator and prey into the air. Breaching is most often associated with ambush attacks. The shark begins deep enough to remain hidden, then accelerates toward the surface. The strike must be timed precisely, too early, and the seal turns too late and the opportunity passes. The final speed is produced by powerful tail beats. The shark's mass continues upward after contact, and the body can clear the surface completely. Water separates from the skin, the fins spread, then gravity returns the shark to the sea. Not every breach includes a successful capture. Some seals escape, some attacks miss by a narrow distance. Young sharks may practice approaches, experience can improve timing, and local hunting techniques may develop around particular colonies. Breaching is only one strategy. Great whites also attack horizontally, approach from behind, or strike near the bottom. The famous leap represents seconds from a much longer search, hours of movement, a short acceleration, and one sudden event. Documentary images often show the climax. The ocean holds the waiting before it, and the silence after. Chapter 14, The Ocean Around a Seal Colony. A seal colony creates a concentration of life. Animals enter and leave the water, young seals learn to swim, and adults return from feeding. Great white sharks patrol beyond the surf zone. They may remain deeper during bright conditions, using the surface as a background for silhouettes. Seals reduce risk through speed and awareness. They travel in groups, remain close to rocks, and avoid predictable routes. A seal that sees the shark early has an advantage. Its body turns more sharply, and it can reach shallow water where the larger predator cannot follow. The shark relies on surprise, dark depth, bright surface, and sudden acceleration. The environment becomes part of the hunt. Some sharks return to the same colony across years. Photo identification can recognize scars and fin shapes. Repeated visits reveal individual patterns. Hunting success varies. A large, experienced shark may choose particular angles. A younger animal may approach too visibly. The colony also attracts researchers. Boats, cameras, and tags record brief encounters, but most hunting remains unseen. The relationship between seal and shark shapes behavior on both sides. Predators influence when prey enters water. Prey influences where predators wait. Neither animal controls the shoreline completely. Each survives through a balance of risk, and the colony continues season after season. Chapter 15, Mistaken Identity and Human Encounters. Great white sharks are capable of injuring humans. Their size and teeth make any close encounter serious, but people are not their normal prey. Many bites are investigative or mistaken. A surfer at the surface may create a silhouette unlike any natural prey, but the shark may still approach to examine it. Sharks do not have hands. The mouth is one of the ways they investigate unfamiliar objects. A single bite can still cause severe damage. In many incidents, the shark bites once and leaves. This differs from the repeated feeding pattern used on normal prey, though every event is different. Risk varies by place and activity. Murky water, feeding wildlife, schools of fish and seal colonies can increase shark presence. Local warnings reflect these conditions. Public fear is shaped by rare dramatic events. News coverage can make attacks appear more common than they are, while the daily presence of sharks remains invisible. Millions of people enter the ocean. Only a very small number encounter great whites directly. Most sharks avoid close contact. Understanding does not remove risk. Large predators require respect, but fear alone creates an incomplete picture. The same animal capable of a dangerous bite also spends most of its life traveling without interacting with people. It crosses open ocean, follows prey, and disappears into depth. The great white is not harmless, and it is not a creature searching for humans. It is a specialized marine predator responding to its environment. Chapter 16, The Great White and the Orca. Great white sharks are powerful predators, but they are not without enemies. Orcas can hunt them. In some regions, the arrival of orcas changes white shark behavior. Tagged sharks have left feeding areas quickly and may remain away for weeks or months. Orcas are intelligent social hunters. They can cooperate, learn specialized techniques, and target specific prey. Some attacks on great whites focus on the liver. The organ is large and rich in energy, and orcas may remove it with remarkable precision. A shark detecting orcas may leave the area. The response can reshape the local food web. Seals gain temporary relief from shark predation. The encounter shows that predator status is relative. A great white dominates many hunts, but another hunter can reverse the balance. Direct observations are still limited. Each event provides new information, and behavior may differ between orca populations. The ocean contains overlapping layers of risk: shark, seal, orca, and fish. Every species responds to threats above and below it. A great white leaving a coastline may travel rapidly, crossing deep water and abandoning a productive feeding site. Power does not eliminate caution. Survival depends on recognizing stronger danger, then moving before contact occurs. Chapter 17, Diving into Darkness. A great white at the surface can descend hundreds of meters. Light fades quickly, and the water becomes colder. Pressure increases with depth, but the shark's body contains no gas-filled swim bladder. This reduces problems created by compression. The eyes adjust to dim conditions, the lateral line detects movement, and electroreception remains effective at close range. Deep water can contain squid, fishes, and drifting carcasses. Prey changes between day and night, and some species rise toward the surface after sunset. The shark may follow these vertical movements, descending during one part of the day, returning toward warmer water later. At depth, the ocean appears empty, but sound travels, particles drift, and living bodies produce electrical signals. Regional endothermy helps protect performance. Warm swimming muscles continue working, even as surrounding temperature falls. A dive may last minutes or much longer. Tag records show depth, but they do not always reveal the exact purpose. The shark reaches the lower point, turns, and begins climbing through dark water. Blue light slowly returns, the surface brightens above, and the predator enters the upper ocean again. Chapter 18, The Great White at Night. Night changes the ocean, the surface loses color, and many animals begin moving upward from depth. Schools of small fish gather beneath faint moonlight, squid rise, and predators follow. A great white continues swimming, its silhouette disappears against dark water, and vision becomes only one part of the hunt. Smell and pressure detection become increasingly important. A struggling fish creates vibration, a distant feeding event releases scent. The shark turns toward the signal, tail movements become stronger, then slow again. Not every investigation ends in feeding. The source may be too small, too distant, or already gone. Moonlight can outline the surface from below. A seal, bird, or floating object becomes visible. The shark watches from depth. Night is not complete darkness. Bioluminescent organisms flash in moving water. Stars reflect across calm seas. The great white moves through all of it, a large body in a world of small signals, reading pressure, scent, and light. Dawn eventually returns, the upper ocean brightens, and another cycle begins. Chapter 19, Scars, Parasites, and Daily Survival. A great white's body often carries marks, scratches along the flank, bite scars near fins, and lines from fishing gear. Some wounds heal, skin closes, and pale scar tissue remains. Other injuries affect movement. A damaged fin changes control. A deep wound can become infected. Parasites also live on sharks, some attached to skin or gills, others live within internal organs. Small fishes may follow large sharks. Pilot fish and remoras can feed on scraps or parasites. The relationship varies by species. A remora uses a modified suction disc to attach. It travels with the shark, saving energy between feeding opportunities. The shark may rub against objects or move through areas used by cleaner fishes, but cleaning behavior in great whites is less visible than in reef species. Much remains difficult to observe. Daily survival includes more than hunting. The animal must avoid injury, maintain movement, and respond to changing temperature. A scarred shark has survived previous encounters, each mark records an event, but the exact story is usually unknown. The ocean removes evidence quickly, blood disperses, tracks do not remain, and most struggles are never seen. Chapter 20: Researching a moving predator. Studying great white sharks is difficult. They travel far, spend long periods below the surface, and cannot be observed continuously. Researchers use several tools: photo identification, satellite tags, acoustic transmitters, drones, and genetic sampling. Each reveals a different part of the life cycle. A dorsal fin can contain unique notches and scars. Photographs allow individuals to be recognized. Repeated sightings build long-term histories. Acoustic tags send coded signals. Underwater receivers detect them when the shark passes nearby. A network of receivers can reveal coastal movement. Satellite tags record location, depth, and temperature. Some transmit when the shark reaches the surface. Others detach later and send stored information. Drones allow observation from above. They can record sharks near beaches, measure distance, and reduce disturbance. Tissue samples reveal genetics and diet. Chemical signatures can show where an animal has fed, and relatedness can connect populations. No single method provides everything. A tag may fail. A photographed shark may disappear for years. The gaps are part of the science. Researchers combine incomplete records, then revise conclusions as new data appears. The great white remains difficult to follow. Technology extends observation, but the animal still spends most of its life beyond direct view. Chapter 21: Conservation and Fishing Pressure. Great white sharks face threats across their range: targeted killing, accidental capture, and decline of prey. The level of danger changes between regions. Their slow growth and late maturity increase vulnerability. A population cannot replace adults quickly. Even a small number of deaths can matter. Fishing gear does not need to target great whites to catch them. Longlines, gillnets, drumlines, and trawls can entangle or hook sharks. Juveniles near shore may be especially exposed. Some animals are released alive, others die before gear is checked, and injuries can continue after release. Legal protection has improved in several countries. Direct hunting is restricted, but enforcement and accidental capture remain important. Protecting migration routes is difficult. The sharks cross national waters, then enter areas governed by different rules. Conservation also depends on public understanding. Fear can support lethal control, while reliable information can encourage safer coexistence. Monitoring populations takes time. Sharks may be absent from a site because they migrated, not because the population disappeared. Long-term data is essential. Repeated surveys, tagging, and genetic studies. Trends become visible only across years. The future of the great white depends on more than one protected beach. It requires cooperation across coastlines, fisheries, and open ocean. Chapter 22: Ecological Role. Great white sharks occupy a high position in marine food webs. They influence prey through direct feeding and through the risk created by their presence. Seals may change routes, timing, and resting behavior. Fish may move away from feeding events. Other sharks may avoid areas occupied by larger individuals. The full ecological effect is complex. Ocean systems contain many predators, and prey numbers are also shaped by climate, fishing, and disease. A top predator does not control every part of the ecosystem, but it can influence several connections, especially where feeding is concentrated. When a great white feeds on carrion, it removes tissue, then smaller scavengers continue the process. When it kills living prey, energy moves from one animal into another, and remains support additional life. Predators can remove weak or injured animals, but they also take healthy prey. The outcome depends on opportunity. Ecological balance is not a fixed condition. Populations rise and fall. Ocean temperature and prey distribution change. The great white is one participant in that movement, powerful, mobile, and adaptable, but still dependent on the wider system. Without prey, migration routes, and suitable nursery habitat, the predator cannot remain. Its survival reflects the health of many connected places. Chapter 23: Myths and Reality. The great white shark has become a symbol of ocean danger. Films, headlines and stories often present it as an unstoppable hunter. The real animal is more complex. It is powerful, it can injure or kill large prey, and close encounters require caution. But it also fails hunts, avoids stronger predators, migrates across empty ocean, and spends long periods without feeding. It is not constantly attacking, most movement is travel, search and adjustment. The dramatic strike occupies only seconds. The shark is not guided by anger, it responds to scent, motion, hunger, temperature and risk. Human ideas of cruelty do not describe its behavior. It is not invulnerable, fishing gear, orcas, injury and habitat change can kill it. Large size does not remove danger. The species is not identical everywhere. Different populations travel along different routes, use different prey and face different threats. Even individuals vary, some approach boats, others remain distant. Replacing myth with biology does not make the shark less impressive. It reveals a more remarkable animal, one shaped by millions of years of ocean life. The real great white is not a monster, and it is not harmless. It is a specialized predator living within limits. Chapter 24: A whale carcass in open water. Far from shore, a dead whale drifts near the surface. Its body has become a floating island of food, scent spreads through current. A great white arrives from deep water, then another, and several sharks begin circling. The largest individual approaches first. It opens the jaws, removes a heavy section and turns away. Smaller sharks wait, space opens, then they move closer. The feeding event continues for hours, oil spreads across the surface, seabirds gather overhead. The carcass provides enormous energy, far more than a single fish, and the sharks can feed without a chase. Bite after bite changes the body, tissue separates, and pieces sink toward deeper water. Below, smaller fishes gather, invertebrates will use what reaches the bottom. The whale supports life at every depth. The great whites eventually lave, some full, others returning later. The carcass remains, drifting, sinking and feeding the ocean, a death becoming hundreds of meals. Chapter 25: Crossing the continental shelf. The coastline falls away beneath the shark, shallow sand gives way to the edge of the continental shelf, then depth increases sharply. The great white continues outward, surface water remains warm, but cold darkness rises below. Schools of fish gather near the shelf edge, currents bring nutrients upward, and predators follow the abundance. The shark dives along the slope, passing through layers of temperature, its muscles remain active in the cold. Light fades, the bottom is no longer visible, and the animal enters open water. A school of tuna moves ahead, fast, streamlined and alert. The shark changes direction. The chase is brief, the tuna turn together and the shark loses the advantage. It continues along the shelf, not wasting energy. The search resumes. Ocean geography shapes movement. Ridges, canyons, shelf edges and currents, invisible structures guide life. The shark follows that structure, a traveler within a three-dimensional landscape where depth matters as much as distance. Chapter 26: Return to the coast. Months after leaving, the great white approaches the coast again. Water becomes shallower, and familiar prey returns. The shark crosses the continental shelf, passes schools of fish, and follows current toward rocky islands. Seals gather along shore, young animals enter the water, and the seasonal hunting ground becomes active. A dorsal fin appears briefly at the surface, then disappears. The shark continues below. Researchers recognize the individual from photographs taken years earlier, a notch along the fin, a scar behind the gill. The return reveals memory and repeated movement. The animal has crossed open ocean, then found the same coastal region again. It may remain for weeks, fade, then leave as prey distribution changes. The coastline is only one chapter, the open ocean another, the deep dives another still. No single location contains the complete life of the great white. The animal connects them through travel, carrying energy and experience between habitats. The shark moves beneath the island, the surface darkens with evening and another hunting cycle begins. Chapter 27, The Last Light Over the Ocean. The sun lowers toward the horizon, orange light spreads across waves, and the water below becomes blue-gray. A great white moves beyond the reef, its back merges with depth, its underside catches the last light. Small fish gather near kelp, seals return toward rocks, and seabirds settle along cliffs. The shark does not rush, its tail moves with steady rhythm, each sweep carries the body forward. The senses remain open, smell across current, pressure through the lateral line, and faint electrical signals near the snout. A shape moves above, the shark turns slightly, then continues without striking. Hunting is selective, energy, distance, risk, and opportunity. Every approach is part of a larger balance. Darkness spreads from the deep water upward, the surface loses color, and stars appear above the ocean. The great white passes beyond sight, no track remains, only disturbed water closing behind it. The predator continues into night, a moving body within a moving sea, and the documentary journey approaches its end. Chapter 28, An Ancient Lineage. Long before modern coastlines took their present shape, shark ancestors were already moving through ancient seas. The great white belongs to a lineage shaped by hundreds of millions of years of change. The species itself is far younger than the earliest sharks. Its closest history is connected to a group of fast predatory mackerel sharks. Fossil teeth provide much of the surviving evidence. Shark skeletons are made mainly from cartilage. Cartilage usually decays before it can fossilize. The hard enamel-like coating of a tooth is far more likely to remain. A single tooth can reveal shape, cutting style, and approximate body size. Groups of teeth reveal how replacement rows were arranged. Sediment around them can establish age and habitat. The serrated teeth of the modern great white are suited to cutting large prey. Earlier relatives show different combinations of shape and edge. Those changes reflect diets that shifted through geological time. The great white is sometimes described as a direct descendant of the giant megalodon. Modern evidence points instead towards separate branches within the broader shark family. Similar teeth do not always mean a direct line of descent. Megalodon occupied warmer oceans and reached far greater size. The modern great white developed within a changing world of marine mammals and cooler seas. Its success came from a different balance of speed, heat retention, and mobility. As whales and seals diversified, large predatory sharks encountered new sources of energy. Natural selection favored bodies able to cross distance and attack powerful prey. Climate repeatedly altered ocean temperature and circulation. Coastlines moved as sea level rose and fell. Populations survived by following suitable water and food. The result is not a primitive animal left unchanged. The great white is a modern species with specialized anatomy. Its ancient appearance hides a long history of adaptation. Every living shark carries that history in muscle, skin, and tooth. The design was not produced for spectacle. It emerged through countless ordinary acts of survival. The animal passing beneath a boat today belongs to the same natural process recorded in stone, an ancient lineage continuing in a modern ocean. Chapter 29, The Juvenile Coast. In a shallow coastal bay, warm water covers sand, rock, and scattered beds of eelgrass. A young great white patrols several meters below the surface. The shark is far smaller than the largest adults. Its body is slimmer, and its diet is different. Seals are not yet the main source of food. Young great whites feed on fishes, rays, and smaller sharks. These prey require precision rather than overwhelming force. The juvenile learns through repeated approaches. A ray lies partly buried beneath sand. Only the eyes and breathing openings remain visible. The shark's electroreceptors detect signals hidden from sight. The approach is controlled. The shark turns before reaching the ray's defensive tail. Experience begins with unsuccessful attempts as often as successful ones. Nursery areas provide more than warm water. They contain abundant prey and fewer large adult sharks. The combination can improve the chances of early survival. A nursery is not a place of parental care. The mother does not remain to guard the young. Each newborn enters the coastal environment independently. Juveniles may stay within broad regional zones for months. They still travel along beaches, bays, and the continental shelf. Their movements respond to temperature and food. This brings them close to fishing activity. Gillnets, hooks, and nearshore gear can capture young sharks accidentally. A population loses future adults when juveniles disappear. Drones now reveal how often young sharks pass near swimmers without incident. Most remain beneath or beyond the people above. Their presence was once less visible than it is today. As the juvenile grows, its range expands and its prey becomes larger. The shallow bay becomes one stage in a much longer migration. The young shark turns toward deeper water, sand gives way to the darker edge of the shelf, and the protected years begin to end. Chapter 30, at the edge of the kelp forest. A kelp forest rises from a rocky seabed. Long blades bend with swell and current. Fish move through a maze of shadow and green light. The great white remains near the outer edge. Its body is too large for the tightest spaces. The boundary between kelp and open water becomes a place of opportunity. Seals use the forest as cover. They turn sharply between stems and rocks. The shark performs best where the water opens. A seal leaving the kelp must cross a brief exposed distance. The shark patrols below that route. Its darker back blends with depth. The attack does not begin immediately. The predator circles and tests angle, current, and light. A poor position would reveal it too early. Kelp also changes water movement. Dense plants reduce current inside the forest. The outer edge contains turbulence, scent, and drifting debris. Fish schools gather where nutrients rise. Smaller predators follow them. The great white enters a food web containing many hunters. The kelp itself depends on cold, nutrient-rich water. Marine heat waves can thin or remove entire forests. Loss of structure changes where prey can hide. Sea urchins may expand when their predators decline. They consume the holdfasts and lower blades. A rich forest can become an open barren. The great white does not depend on kelp in the way a reef fish does, but it responds to the life concentrated around it. Changes at the seabed can influence a predator near the surface. A seal appears between two stands. It detects the shark and turns back before the final rush. The encounter ends without contact. The great white continues along the forest edge. Open water lies on one side and dense cover on the other. The patrol follows the shifting boundary. Chapter 31, the Sardine Run. Along a productive coastline, cold, nutrient-rich water meets warmer current. Millions of small fish gather into moving schools. The school behaves like a single changing body. Each fish responds to the speed and direction of its neighbors. A turn can spread through thousands of animals in seconds. Dolphins drive from below, seabirds strike from above, larger fish attack through the sides. A great white enters the gathering. It is one predator among many. The abundance of prey does not make capture automatic. The school tightens when danger approaches. A compact bait ball reduces the chance that any one fish will be selected. Confusion becomes a form of defense. The shark accelerates through the edge. Its jaws close on empty water. The fish separate and reform behind it. A second approach comes from below. This time the shark targets an individual pushed away from the group. Isolation removes the protection of the school. Small prey provides less energy per capture than a seal, but a dense seasonal event can offer repeated chances. Predators adjust to what the ocean provides. The run also supports animals that never meet the shark. Scales, waste, and dead fish sink. Deeper communities receive the remains. Currents determine where the gathering forms. A shift in temperature can move the entire event offshore. Predators must search a coastline that changes from year to year. By evening, the school spreads. The concentrated feeding scene dissolves across open water. The shark returns to solitary travel. For a few hours, the coastline held one of the ocean's largest temporary gatherings. Then current and movement carried it away. Chapter 32, the mechanics of acceleration. A great white can travel with slow, economical tail beats, but an attack demands a different use of the body. Steady movement becomes sudden acceleration. Power begins in deep muscles along the trunk. Contractions pass from side to side. The crescent-shaped tail transfers that force into water. The narrow region before the tail acts like a strong hinge. It allows rapid movement without excessive bending through the entire body. Energy remains focused at the rear. The pectoral fins control lift and angle. Small changes alter depth during the final approach. They also stabilize the body against rolling. Regional endothermy keeps swimming muscles warmer than surrounding water. Warm tissue can contract with greater force. This becomes important during a short high-speed strike. Acceleration cannot continue indefinitely. Powerful movement consumes energy and produces heat. The shark must choose when the effort is worthwhile. Turning creates another challenge. A large body carries momentum. The tail, fins, and flexible spine redirect it through a curved path. Seals exploit this difference. Their smaller bodies can change direction more sharply. A detected attack may become a contest of turning rather than speed. The shark may overshoot, then circle and approach again. Not every failed strike ends the hunt immediately. Researchers estimate movement using video, tags, and scale references. Exact top speeds remain difficult to measure in open water. Short bursts are easier to describe than to record. The famous breach is the visible result of this machinery. Most of the acceleration occurs below the surface. Only the final momentum enters the air. After the strike, the tail returns to a slower rhythm. The body shifts from explosive power back to efficient travel. Chapter 33: Layers of Temperature and Oxygen. The open ocean is divided into invisible layers. Temperature, oxygen, and salinity change with depth. A shark moving vertically crosses several habitats. Near the surface, sunlight warms the upper water. Wind mixes it into a relatively even layer. Below lies the thermocline. Temperature falls more rapidly across a narrow depth range. Many animals gather along this boundary. Small fish may remain where food and temperature are favorable. Squid move through the layer during daily migrations. Predators follow the concentration. A great white can descend into colder water. Its warmed muscles retain performance, but temperature still influences how long it remains. Oxygen can also decline with depth. Some regions contain broad oxygen minimum zones. Animals are compressed into the water above or below them. This creates a vertical landscape. The most useful depth changes through the day. Prey distribution can be more important than distance from shore. Tags record these repeated dives. A line on a graph reveals descent and ascent, but not every feeding attempt between them. The shark may pass through several hundred meters of water. Pressure increases while light disappears. The body remains free from the problems of a gas-filled swim bladder. At the lower point, the shark turns and begins climbing. Warmer blue water slowly replaces the cold darkness. Ocean warming can change the depth of these layers. Oxygen patterns may shift as circulation changes. Prey and predators respond together. The great white does not experience the sea as one uniform space. It moves through stacked environments. Each one offers a different balance of food and cost. Chapter 34: Reading the Earth's Magnetic Field. A migrating great white may cross open ocean without a visible landmark. The route can continue for weeks. Navigation requires information beyond the horizon. The Earth's magnetic field forms one possible guide. Its strength and angle vary across the planet. Animals may detect these regional differences. Evidence from several shark species suggests sensitivity to magnetic cues. The exact biological mechanism remains under investigation. Electroreception may be connected to the ability. A moving conductor within a magnetic field can produce weak electrical effects. Seawater and the shark's own movement may create detectable signals. The ampullae of Lorenzini are sensitive enough to register minute changes. Magnetic information would not work alone. Current, temperature, smell, and the position of the sun may all contribute. Navigation is likely built from several systems. Memory also matters. Some sharks return to the same seasonal feeding regions. Repeated journeys can refine the route. The path is not always a straight line. A shark may follow fronts where water masses meet. Food can redirect migration. Storms change surface conditions. Clouds hide the sun and current shifts. A magnetic reference would remain available below. Researchers test orientation using tags and controlled magnetic fields. Results reveal ability without describing every natural decision. Open ocean navigation remains partly hidden. The great white continues across deep water. No reef or coastline lies beneath it, yet the movement is not directionless. Months later, the same shark may appear near a familiar island. Its arrival connects distant points through an unseen map. The ocean offers few fixed signs. The planet itself may provide one, a field passing silently through water and living tissue. Chapter 35: The Offshore Night. After sunset, the upper ocean changes as countless small animals rise from depth. This is the largest daily migration on Earth. Lanternfish, squid, and drifting invertebrates move towards surface food. They avoid bright daylight by remaining deep. Darkness reduces the risk from visual predators. The great white crosses this rising layer. Its path intersects a community hidden during the day. The open ocean becomes crowded with movement. Bioluminescent flashes appear around disturbed water. Some animals produce light to communicate or confuse predators. Others use it to match the faint glow above. A squid accelerates and releases ink. The shark turns but does not continue the chase. The energy return is too small for a long pursuit. Farther ahead, a school of larger fish follows the same migrating prey. The great white changes depth to investigate. Night does not remove vision. Moonlight and starlight still create silhouettes near the surface. The eyes work together with smell and pressure detection. Sound travels through darkness. A feeding event creates irregular vibration. The shark follows the disturbance before seeing its source. Near dawn, the small animals begin descending. The living layer sinks away from growing light. The shark follows part of the descent, then levels within cooler water. Its movement reflects prey rather than the clock alone. From a ship, the surface may appear empty throughout the night. Most of the activity remains several meters below. The great white passes beneath the vessel, a large predator among billions of smaller travelers, and the offshore night closes above it. Chapter 36: Encounters with other sharks. The great white shares the ocean with many other sharks. Blue sharks cross open water. Shortfin marcos pursue fast fish along current boundaries. These species do not occupy identical roles. Body size, temperature tolerance, and hunting style divide the habitat. Overlap still occurs around abundant food. At a whale carcass, several shark species may gather. The richest feeding event temporarily concentrates animals that usually remain apart. A large great white approaches with confidence. Smaller sharks move away from its path. Body size often establishes priority without a direct fight. Posture can signal rising tension. A lowered pectoral fin or abrupt turn changes the encounter. Distance prevents many injuries. A bite between large sharks can cause serious damage. Avoidance is usually more efficient than combat. The ocean provides room to separate. Young great whites face greater risk. Larger sharks may prey on juveniles. Nursery habitat reduces but does not eliminate that danger. Competition also occurs without contact. Two predators may follow the same fish school. The first successful hunter removes opportunity from the other. Marcos are capable of remarkable speed. Great whites carry greater mass and cutting power. Each design performs best under different conditions. Scars on adult sharks sometimes reveal previous encounters. The source of a mark cannot always be identified. Teeth leave evidence without explanation. The gathering eventually disperses. One shark moves toward the shelf, and another offshore. Temporary competition returns to solitary travel. The great white is a top predator, but it exists within a community of other hunters. Power is always measured against context. Chapter 37: Order at a feeding event. A drifting whale carcass attracts several great whites. The scent has traveled through current. Each arriving shark assesses both food and competitors. The largest animal does not need to attack immediately. Its approach alters the movement of smaller sharks. Space opens before the jaws reach the carcass. One shark removes a section of blubber, then turns away to swallow. Another moves into the opening. The sequence can appear organized, but it is created through repeated individual decisions. Size, confidence, and position influence access. A smaller shark may circle for a long time. Waiting avoids a dangerous close encounter. The carcass contains enough food to reward patience. Body language becomes important at short range. Direction and fin position reveal intention. A sudden turn can end an approach. The sharks are not cooperating, they are tolerating one another around an exceptional resource. The gathering lasts only while the food remains. Seabirds feed on pieces at the surface, fishes collect fragments below. The event extends through several levels of the food web. Oil spreads across the water, waves carry small pieces away. The original body becomes increasingly difficult to recognize. Some sharks leave after feeding heavily, others remain and return repeatedly. Individual behavior differs within the same event. When the carcass finally sinks, the surface gathering ends. A second ecological sequence begins in deep water. The great whites move away in separate directions, the temporary hierarchy disappears, and the open ocean becomes solitary again. Chapter 38, Courtship written in scars. Great white mating has rarely been observed directly. Much of what is known comes from anatomy, scars, and reproductive condition. The most important behavior remains largely hidden. Males possess paired claspers. These structures transfer sperm during internal fertilization. Their development helps researchers identify maturity. Females sometimes carry fresh bite marks around the fins and flanks. Mating in several shark species involves the male holding the female. Some white shark scars may come from this contact. Not every bite mark is evidence of courtship. Feeding interactions and conflict can create similar injuries. Interpretation requires caution. Seasonal gatherings may increase the chance of adults meeting. The offshore movements of males and females are not always identical. Migration may include a reproductive purpose. The white shark cafe has generated particular interest. Some males perform repeated rapid dives there. The reason remains uncertain. Females reproduce slowly. Years may pass between litters. A long cycle limits the speed of population recovery. Mating itself may be brief, but the biological preparation extends across seasons. Body condition depends on previous feeding success. Large adult females are especially valuable to the population. They carry the energy required to produce large young. Their loss removes more than one breeding opportunity. Researchers examine hormones and ultrasound images when possible. These methods reveal pregnancy without witnessing conception. Each animal provides a rare part of the process. The ocean offers no nest or visible breeding ground. Adults meet and separate within an enormous range. The event leaves little evidence. Courtship remains one of the least filmed chapters, a major part of the species' life cycle, known mainly through the marks it leaves behind. Chapter 39, Birth into an Independent Life. A pregnant female carries developing young inside her body. There is no placental connection like that of most mammals. Nutrition is provided through a different system. Embryos consume unfertilized eggs within the uterus. This process is known as oophagy. It supports growth before birth. The gestation period is believed to be long. Exact duration remains uncertain. Direct observation is almost impossible. Birth may occur in productive coastal regions. Young sharks appear in nursery habitats, but the full event has not been documented in the wild. A newborn great white is already a capable swimmer. Its senses and replacement teeth are functional. No adult remains to provide food. The young shark must locate prey immediately. Small fishes and rays offer the first opportunities. Failure has no parental safety net. Large size at birth provides some protection. The newborn is still vulnerable to larger sharks. Shallow habitat can reduce encounters with major predators. Growth depends on regular feeding. Temperature influences metabolism. The juvenile follows seasonal changes along the coast. Some young sharks return to the same broad nursery region. Others range across hundreds of kilometers. Individual movement varies from the beginning. Only a portion survive to maturity. Fishing, predation, and food shortage remove many. Those that remain require years to become adults. This slow life history explains the species' vulnerability. thousands of eggs are not released into the sea. Each litter contains a limited number of large young. The newborn moves away from the unseen birth site. Its first journey begins without a family group. Independence is immediate and complete. Chapter 40: A whale fall on the deep seabed. The remains of a whale descend through dark water. Surface scavengers have removed large sections, but enormous energy is still locked within bone and tissue. The carcass reaches the seabed. A cloud of sediment rises. Deep-sea animals begin arriving. Hagfish and sleeper sharks remove soft tissue. Crabs and amphipods enter openings. The first stage is dominated by mobile scavengers. Months later, smaller organisms feed on enriched sediment. The area around the bones contains more life than the surrounding plain. Bacteria begin breaking down fats inside the skeleton. Chemical reactions produce sulfide. Specialized communities use that energy. Tube worms, mussels, and microbial mats may develop. The whale becomes a temporary oasis. Its influence can last for years. The great white never follows the carcass to this depth. Its feeding occurred near the surface, yet the pieces it released contributed to the fall. Energy moves from sunlight to plankton, from plankton to whales, and then to deep-sea life. Predators and scavengers connect distant habitats. The bones slowly lose their stored compounds. The specialized community declines. Ordinary deep-sea conditions begin returning. No part of the event is wasted. What one animal cannot use becomes food for another. Decomposition is a continuation of the food web. Far above, the great whites have already dispersed. The surface shows no sign of the ecosystem developing below. The whale fall remains in darkness, a final chapter in one life, and a beginning for thousands of others. Chapter 41: Noise in the Modern Ocean. The ocean has never been silent. Waves, storms, whales, and moving animals create sound. Modern activity has added powerful new sources. Ship engines produce continuous low-frequency noise. Construction drives intense pulses through water. Sonar can travel across great distance. Great whites detect vibration and low-frequency sound. These senses help locate struggling prey. Artificial noise may enter the same sensory space. The exact effect on white sharks is not fully known. Responses can depend on intensity, distance, and previous experience. Not every sound causes avoidance. A passing vessel may change depth or direction. Repeated traffic can alter how animals use a coastline. The effect may be subtle rather than dramatic. Noise can also affect prey. Fish schools change behavior around engines. A predator experiences the indirect result. Research vessels create their own disturbance. Scientists must separate natural behavior from reactions to the boat. Drones and remote receivers reduce some influence. Acoustic tags rely on sound deliberately. A transmitter sends a coded signal. Receivers identify the shark without continuous pursuit. The method reveals movement while adding only a small local signal. It is one example of technology designed to observe quietly. No method is entirely without effect. As shipping routes expand, more marine habitats experience constant background noise. The long-term consequences remain an active field of study. The great white crosses beneath a cargo vessel. The engine vibration fills the water, then fades as the ship moves away. Natural sound slowly becomes dominant again. Current passes along the body, and the shark resumes its offshore route. Chapter 42: Contaminants in a top predator. A great white feeds high in the marine food web. Energy becomes concentrated as prey is consumed. Some pollutants follow the same path. Persistent chemicals can remain in tissue for years. Small animals absorb low levels. Predators receive larger amounts through repeated feeding. This process is known as biomagnification. Concentration increases at higher trophic levels. Large, long-lived animals can carry significant burdens. Metals such as mercury also accumulate. Levels vary with location, diet, and age. An offshore shark may carry a different chemical profile from a coastal juvenile. Pollutants can interfere with hormones, immunity, and reproduction. The effect is difficult to measure in a wild shark. Sampling opportunities are rare. Researchers analyze small tissue samples, chemical signatures reveal exposure and feeding history. The shark can often be released after collection. Microplastics create another pathway. Small particles enter fish and invertebrates. Predators consume the contaminated prey. The physical particles may pass through, associated chemicals can remain. The total biological effect is still being investigated. Pollution does not remain near its source. Current transports material across borders. A migrating shark encounters the combined output of many coastlines. Reducing contamination requires action before it enters the sea. Cleanup cannot remove every dissolved compound. Prevention protects entire food webs. The great white shows no obvious sign as it swims. Many environmental pressures are invisible. A powerful body can still carry hidden stress. Its tissue becomes a record of the ocean it crossed, not only prey and temperature, but the chemical history of modern water. Chapter 43, Sharks at a Busy Beach. Morning arrives along a populated coastline. Swimmers enter the water. A juvenile great white moves beyond the breaking waves. The shark is present without approaching anyone. It follows fish through a shallow channel. Most encounters between people and sharks end without being noticed. Drones have changed what can be seen. Observers track the animal from above. A beach can be cleared before the shark reaches crowded water. Non-lethal warning systems reduce the need to kill predators. Spotters, aircraft, acoustic receivers, and public alerts work together. Each method covers a different gap. Traditional barrier nets can entangle many species. Sharks, rays, turtles, and marine mammals may be captured. Protection for people can create ecological cost. Newer approaches focus on information and separation. Temporary closures respond to actual presence. Education helps swimmers understand local conditions. Risk is higher near seal colonies. Schools of baitfish and murky water, dawn and dusk, can reduce visibility. Local advice reflects the behavior of a specific coast. No system can remove all danger. The ocean remains a wild environment. The goal is to reduce risk without erasing its predators. Ecotourism can increase appreciation. It can also alter behavior if bait is used carelessly. Management determines whether observation becomes disturbance. A living shark may support research, tourism, and a functioning ecosystem. A killed shark provides none of those future benefits. Public value changes when fear is replaced by knowledge. The juvenile turns toward deeper water. The beach remains open. People continue swimming above a route used for generations. Coexistence does not require pretending the animal is harmless. It requires accurate information and practical caution. Respect becomes more useful than panic. Chapter 44, Healing in Open Water. A great white cannot retreat to a den after injury. It continues swimming through salt water. Every wound must heal while the animal remains active. Cuts may come from prey, fishing gear, or other sharks. Some close rapidly. Others leave pale marks that remain visible for years. Shark skin is protected by dermal denticles. These tooth-like structures reduce abrasion and turbulence. They also create a difficult surface for some organisms to attach. When the skin is broken, blood clotting begins and damaged tissue closes. The exact rate depends on depth, location, and condition. A wound near a fin can alter movement. Even a small change in control increases the cost of swimming. The shark must compensate with the rest of its body. Infection is possible, but seawater contains both harmful and harmless microorganisms. The immune system responds without the shelter available to land animals. Researchers sometimes photograph the same shark across several seasons. Fresh injuries become scars. Repeated images reveal the progress of healing. Not every animal survives a severe wound. Internal damage may remain invisible. A shark can disappear before the outcome is known. The scars carried by older great whites are records of previous risk. Each mark survived long enough to heal. The body becomes a history written across skin. The shark moves beyond the camera. The wound remains part of its movement, and healing continues in open water. Chapter 45, Where Currents Meet. Far from shore, two water masses meet. One is warmer and clearer. the other carries cold nutrients from depth. The boundary is known as an ocean front. It may stretch for hundreds of kilometers, yet its position can shift with wind and season. Plankton gathers where nutrients support growth. Small fish follow the plankton, larger predators follow the fish. A great white approaches the front from warmer water. Temperature changes across only a short distance. The shark crosses and turns along the boundary. The front creates a line of opportunity. Prey is more concentrated than in the surrounding ocean. Searching becomes more efficient. Seabirds often reveal these productive zones. Their feeding activity is visible from above. A shark receives the same information through movement and scent below. Floating debris may also collect along the boundary. Small animals use it as shelter. The front becomes both feeding ground and traveling corridor. Satellite maps allow researchers to compare shark positions with temperature. Patterns show repeated use of certain features. The animals respond to structures that cannot be seen from land. As wind changes, the productive line bends and breaks apart. The shark follows one branch before turning offshore. The ocean appears open and without borders, but current creates temporary roads and gathering places. The great white moves through a landscape made entirely from water. Chapter 46, Caught and Released. A fishing vessel retrieves a longline from deep water. Most hooks were set for other species. One carries a young great white. Accidental capture is known as bycatch. The animal was not the target, but the danger is the same. The shark has continued swimming against the line. Exhaustion builds while movement is restricted. Stress increases before the crew reaches it. Release does not guarantee survival. Hook location, handling time, and water temperature all matter. Internal injury may not be visible. A carefully managed release reduces additional damage. The shark remains in water when possible. The line is removed or cut quickly. Researchers may attach a tag before release. The signal can show whether movement returns to normal. Post-release data reveals outcomes that observation alone cannot. Some sharks resume steady travel within hours. Others remain near the surface or disappear. Each case improves understanding of fishing impact. Changes in hook design and fishing practice can reduce capture. Avoiding known nursery zones also helps. Prevention is more effective than rescue. International fleets cross the same migration routes used by great whites. One animal may encounter several fisheries in a year. Risk accumulates across borders. The released shark turns away from the vessel. Its tail strengthens into a regular rhythm. The line falls behind and open water returns. Extended documentary closing, the predator beyond the surface. Evening settles across the continental shelf. The last sunlight narrows into a silver band above the water. A great white moves below the fading light. Its tail follows the same controlled rhythm used across thousands of kilometers. The body remains almost invisible from the surface. The shark has crossed nursery bays, kelp edges, and open ocean. It has entered cold depth and returned to warm current. No single habitat contains its entire life. Its anatomy connects every part of the journey. Warm muscle supports movement through cold water. Sensitive organs reveal a world beyond direct sight. The teeth receive the greatest attention, but survival depends equally on restraint. Most objects are passed without a bite and most prey escapes. A hunt may occupy seconds. The search before it may continue for days. Documentary images capture the climax more easily than the waiting. The same animal can become hunter, scavenger, and competitor. It can dominate a carcass and retreat from orcas. Power changes with circumstance. Its migrations connect national waters and distant ecosystems. Protection in one region can be weakened by danger in another. The ocean does not follow political boundaries. Juveniles depend on productive coasts. Adults depend on migration routes and seasonal feeding grounds. Reproduction depends on mature animals surviving for decades. This slow life history leaves little room for heavy loss. Fishing mortality, pollution, and habitat change accumulate. Recovery cannot occur as quickly as damage. Research continues to reveal movement and depth, yet courtship, birth, and much of daily life remain unrecorded. The species still keeps most of its history below the surface. That uncertainty is not an absence of knowledge, it is a reminder of the scale of the ocean and of how little time any observer spends within it. The great white turns away from the shelf, shallow sand falls behind, the seabed descends into blue darkness. A school of fish divides around the body, the shark does not pursue, its route continues toward deeper current. Above, waves move toward a distant coast, seabirds settle and fishing boats return to harbor, the predator passes beneath all of them unseen. The outline grows faint, grey back, pale underside and crescent tail merge with the water, only movement separates the animal from the sea. Then even that movement disappears, the surface remains unbroken, and the great white continues beyond observation. Not a monster and not a harmless symbol, but a specialized living predator shaped by ancient oceans and surviving within a changing one. The final light leaves the surface, darkness spreads across the open sea, and the ocean continues.